Okay, so we're going to go into chapter 5 now, differentiation. So this is kind of a recap of everything that you supposedly learned in calculus. But we're going to, of course, we're going to do it, in much greater depth than you've seen it before. Okay. So, so let's start off with differentiability, right? So you have some function, right? You have some function going from R to R, right? And you say you have the function, and there's some point x naught. Well, you say that your function is differentiable at that point. What does differentiable at that point mean? What is differentiability? Anybody remember the definition of differentiability? Talk to a neighbor. Say, I forgot completely. I have no idea. What was that?
Yeah, I remember like the actually, wait, don't matter. Hold on.
Okay, yeah. Anybody want to volunteer their vague recollections of differentiability? What was differentiability, Sandy?
A function is differentiable at a point if there's a limit at that point, the limit equals the value of the function at that point, and the function is continuous at that point.
Well, you're saying that that the limit of the function as you approach that point equals the value of the function at that point? That's what you're saying? Is that what you're saying?
Yes. Well, actually.
So what that means is, like, as you get closer to the point, your values get closer to the actual value at that point, right? So your function could be really. Right, you could have something like this, for example, right? So your values get close to there, but that's not differentiable. That's something else. Yeah. Anybody else want to sort of vaguely, good, but it's okay. That's all right. No problem, right? When I was learning Chinese in college, my teacher said, he said, the key to learning is shamelessness. Right? You just want to throw out whatever nonsense you got and then be corrected, right? And then don't worry about it, right? It's just like how children learn. Why do children learn so quickly? Because they just throw out, they just say all sorts of crazy stuff, and then you correct them, right? And then they learn the language. Yeah,
wasn't it like that? At any given point x, the limit of as h approaches 0 of f of x plus h minus f of x over h equals some n, which is the slope at that point.
Yeah. So that's So it means that, right? If you take, let me sort of draw the picture, right? You have this point. Let's call it. We're calling it x. And you take some tiny, some h. So h is some distance, basically, right? And so what you do is you look at the value of the function, right, at x plus h. I'm sorry, this should be x plus h. H is this little distance here, right? And then you subtract off the value at f of x, and then you divide by, right, h, right? You divide by h, which is to say the difference between the points, right? So you're taking this difference and you're dividing by this difference, right? It's the rise over the run, right? And what it gives you is the slope of the line through those 2 points, right? The slope of the so-called secant line. The secant line through those points, right? And then you let h go to 0, right? You let h go to 0. So you're taking, the slopes of these secant lines as the second point approaches the first point, right? Sometimes people, so let me just put the h on the bottom like this. It's just the same thing, exactly the same thing to say f of, let's say t minus f of x over t minus x as t approaches x, right? Right? So, definition, we say f is differentiable at x if this limit exists, right? If either of these limits, if the limit blah exists, right? Those are the same limit, so I'm just going to say the limit, right? In which case, right? In which case, we write f prime x is that limit. Right, the derivative of f at x is going to be that limit. Right, and the idea is that you're taking this you're taking this second point, you're letting it approach the first point, and if the limit exists, it basically tells you that that you can get a slope of the tangent line through that point. Right? So geometrically, one can get the slope of the tangent line, the so-called tangent line, at that point. Okay. Okay, so that's probably how you saw it. You saw it in calculus, right? So let me sort of mess around with it a little bit. Now we're going to mess around with it and make it look a little bit different. Okay, so right, equivalently. F differentiable at x means the same thing as saying that there exists a number f prime x. Okay, so there exists some number f prime x such that here comes f of x minus f of t minus f of x over t minus x minus f prime x equals 0 as t approaches x. Okay, so you should be like, what was that? Is that? We haven't done anything, right? We just subtracted we just moved the number to the other side. Okay. Okay. Let me denote this thing in the box by u of t. Okay. Okay. And then I'm going to rewrite it again. I'm going to say equivalently, there exists a number f prime of x and a function u of t such that f prime of x, f of t minus f of x over t minus x equals f prime of x plus u of t, and the limit of u of t is 0 as t approaches x. Yeah, Rishi.
What's like the domain of u here?
T is just anything really. It could be all of R.
Okay.
Yeah. Yeah. Right. T is your second point. Right.
Yeah, sure.
T is the second point. So u of t can be anything. Okay. Okay. So I've done nothing. Right. I've just taken this thing and I said, let's call this thing u of t. Right. U of t is this function defined like this. Right. U of t is defined to be this thing minus that thing. Right. And so yeah, I've just put some notation on it basically. I'm calling this thing u of t. Okay, so let me rewrite it one more time. There exists f prime x in R and function u of t such that f of t equals f of x plus f prime x t minus x plus u of t minus x, and the limit of u of t equals 0 as t approaches x. Okay. So this is exactly the same statement that we have over here, right? I've just altered it like tiny bit by tiny bit. I'm just like sort of like just rearranging it and giving things names here. So okay. So now I'm gonna sort of block things out here. So I'm going to think of this, I'm going to separate this into two parts. Right? I'm going to say, in other words, f of t can be expressed as this guy plus that guy. Okay? Turn to a partner and say, that first thing is just
It's like the
And then it's the slope times.
Oh.
It's the
it's like if you're just like that's like a linear part.
okay. Let me call it L of x, right? L of x is going to be this guy. Right? So what is L of x? Somebody want to say? I'm ignoring you guys. Somebody other than regulars, and Izzy, you're also bent.
Yes.
Number 3.
Sandy?
The linear approximation of f of t.
Exactly, right? So it's a function that, what is it? It's a function that at x, right, takes on the value f of x, right? So it has the same value at x as f of x, and it's a linear function, right? It's a linear function with slope f of x, f prime of x, excuse me. It's a linear function with slope. So if my function looks like this, then the slope of L is the same as the slope of the tangent line. In fact, it is the tangent line. Okay, so this L guy here is the tangent line, right? Tangent line to f at x. Right, or its graph is the tangent line if you want to be, pedantic about it. It's the linear approximation, its graph is the tangent line. Okay, So what does differentiability mean? Differentiability means that your function is basically the tangent line, right? Your function is basically the tangent line plus something that goes to 0, right? Plus some sort of, you want to think of this guy as the error. Okay, your function is basically the tangent line. Differentiability means that there's a line that approximates your function so well that the error vanishes as you go to x. In fact, it vanishes so well that even if you divide by something that goes to 0, it still goes to 0. Okay, this is key. Okay, look, it's not just that the error goes to 0, right? Because, look, I could say, look, this function here, I've got a linear approximation of it, and the error goes to 0. Right? As I get close to my point, the error goes to 0. Differentiability, no, right? That's not differentiability, right? The error has to go to 0 in a very fast way, right? Even when you divide by this term, this first order term that goes to 0, the resulting thing still goes to 0. Okay, so it goes to 0 in a particular way. Okay, so that's what differentiability means. Okay, that's how you want to think about that's one way of thinking about differentiability. That this is very good. This is fine. But another way of thinking about it is that differentiability means that there is a line that approximates your function so well that the difference between your function and that line goes to 0 in a very fast way. Okay, in this particular fast way. Okay, everybody okay? Okay, so that's the way we're going to think about it. My old PhD advisor, Bob Pfefferman, often would say, morally speaking. Morally speaking, this is this. So I think probably in this case he would say, what does differentiability mean? It means morally speaking, your function is aligned. Okay, that is infinite on the infinitesimal scale, your function is aligned, right? So, right, as you get close, as you zoom in closer and closer, right, as your scale zooms in closer and closer, right, your function may very much not be aligned. It might not be aligned at all, but as you zoom in closer and closer, it becomes more and more line-like, right? Whereas, something like this, no matter how far you zoom in, it never becomes line-like. I once read an article. No, one article that I often read is by William Thurston. It's called Proof in Progress in Mathematics. And in it he talks about developing different models for different concepts, right? So you can think of the derivative in this way. You can think of the derivative in that way. You can think of the derivative in terms of a microscope zooming in and turning into a line, this sort of thing. And he talks about in the article he says, so one afternoon I sat down and started writing my different ideas of what the derivative was. Here is number 36 or 37 or something like that. So he had so many different ways of thinking about of understanding how this idea works. And I think that's really something that we want to keep in mind, right? You kind of want to have different ways of looking at the same concept, different ways of does it actually work? Well, if from this model's point of view, if I do this, I see that oh, this thing will fall over here, and then this thing will happen, right? So you want to have kind of a internal construct or multiple internal constructs of ideas. Yeah. If I may say something amusing, I think. Thurston was my thesis advisor as an undergraduate, and he was famous for like being able to see in higher dimensions. And so, like, I came in one day and I said, okay, you know, Professor Thurston, I'm thinking about my project, and I have this. This is the thing I'm thinking about. And he says, yes, I see it. It goes something like this. And he says, can you see that? You know, I never understood anything he said. Yeah. Okay. Yeah, hopefully you guys can understand me more than I understood him. But you know, he was one of those like super genius type people. He's one of those people for which, about whom they tell, you know, the kind of story, like the story about, you know, Thurston. He's an undergraduate, I think at Reed College. He comes in late to class as usual. He sees a bunch of problems on the board. He writes them all down, and then he goes home. He comes back the next week and he says, Professor, those were really hard problems. You know, I was only able to solve like 3 of them or something like that. And the professor says, those were unsolved problems. Yeah, but I've heard that story about other mathematicians as well, so I don't know if that one is true or not. But okay, so differentiability, right? Now let's use. It's not going to be the most exciting thing, but we're going to reprove some of the things that you saw as an undergrad. You are undergraduates. As a child, as a younger child, in your calculus class about differentiation. So like properties of differentiation. Yeah, properties of differentiation. So the first one is that. As you probably know, if f is, so again, in this section we're basically always going to have a function from R to R. Okay. If f is differentiable at some point x, then what am I going to say? Differentiability implies, go ahead, Rishi.
It's continuous.
Continuity, right? So differentiability implies continuity. Continuous at x. Okay. So, right, we want to show that the limit of f of x as x approaches, the limit of f of t as t approaches x is f of x. Right? Or equivalently, that the limit of f of x minus f of t minus f of x as t approaches x is 0. Okay. So anybody remember how to prove this? Anybody see how we would get from differentiability to continuity? So one way we could do it is by playing the game that I said I brought up a couple days ago of trying to squeeze in the information you have in order to simplify the problem, right? So like what we have is differentiability, right? We have that the limit of f of t minus f of x over t minus x as t approaches x is some number, right? And we're trying to show that the limit of f of t minus x is equal to 0, right? So kind of like just as a game, you know, if we're trying, this is the thing that we have control over, right? This is the thing we have control over. We know it turns into a number, right? This is the thing we're trying to control, right? So how do we squeeze in the thing that we're trying to control? Well, we're going to divide by t minus x, right? And of course, you can't just divide by numbers whenever you feel like it, but you can always multiply by 1, right? So the proof is, you say, this thing is the same thing as this thing. Right? We can always multiply by 1. Right? So just as last time we had a cleverly chosen 0, now we have a cleverly, not really that cleverly, chosen 1. Okay. So now think. Now the limit of f of x, sorry, f of t minus f of x over t of x as t approaches x, and the limit of t minus x as t approaches x, both exist. Right? Both those things exist. And we have this theorem, like I think I called it like limits and arithmetic or something like that, which said that if the limits exist, then you can change the order of you can interchange limit and arithmetic operation, right? So here we can, that says that the limit, sorry, the product of the limits, since both of them exist, the product of the limits equals the limit of the products. Right? Right, this thing, of course. This thing, right? The product of the limits equals the limit of the products. And so this thing that we have over here, right? This thing that we have over here actually equals the limit of this times the limit of that. Well, the limit of this is f prime of x, and the limit of this is 0, right? And so we get 0. Okay, everybody all right so far? Anybody feeling? Yeah, Izzy.
How do we know the limit of t minus x exists again?
Well, you know, as t approaches x, you know, it's you know, the limit. Let me just say it this way. Right, if I ignore this x is constant, right? This is basically saying that the limit of t as t approaches x is x.
Okay.
Right, which I'll leave it to you to prove.
Split up the subtraction one more time.
Yeah, it's okay. So, and other questions? Okay, so that's one way to prove it, right? That's one way to do it. But you might complain and say, look, we just created this other interpretation of differentiability. Why didn't we use the other interpretation of differentiability? Let's prove it using the other interpretation of differentiability. Okay, so proof number 2. Okay, so f differentiable at x, as we said, is the same thing as saying that f of t equals f of x plus f prime x t minus x plus u of t minus x, where u of t goes to 0, right? As t goes to x. right? And so the limit, right? Remember what we're trying to show. We're trying to show that the limit of f of t as t approaches x is f of x. So take the limit as t goes to x. Right? What happens to this term? As t goes to x? Nothing. That's just f of x. What about this term? F prime x is just a constant. As t goes to x, goes to 0. What about this guy? Goes very much to 0, right? It goes to 0 squared, right? So we get plus 0 plus 0 squared. Well, that's just f of x. Right? Okay. So I like this proof lots better than the other proof. This proof is sort of like some sort of algebraic gamesmanship. This proof says differentiability means that you're basically a line. Lines are continuous. Right? Right? So, right, like which one gives you the intuition? That one. To me, that one does. Okay. So now let's do some other properties. Yeah. Okay, so other basic properties. Differentiation and arithmetic. Wait, were there any questions about the second proof? Okay. Okay, so differentiation and arithmetic. Say that you have two functions, f and g, that are differentiable at some point x naught in AB, then the derivative of the sum, right? Then the derivative of the sum equals the sum of the derivatives, right? The derivative of the product is not equal to the product of the derivatives, but rather the first guy times the second guy's derivative plus the first guy's derivative times the second guy. And then you have the quotient, you have a quotient rule, etc., etc. So things that you saw and used before. Okay. So this is telling you about the interaction between differentiation and arithmetic operations. Okay, so let's do the first one. No. I'm going to let you do the first one. Take a minute, 2 minutes, and write down the proof of the first one using the line-like morally aligned definition. Okay, let's do it. Okay, so we have from the beginning we have, so we know that f and g are differentiable at x. So in other words, we know that we can write f of x as f of x naught plus f prime x naught x minus x naught plus u of x minus x naught, right? For some u that goes to 0 as x goes to x naught, right? And we know that we can do the same thing for g, right? For some, we have some other function, v, the error function, right? Okay, and we want to show that we can do such a thing for f plus g, right? Want to show can do it for f plus g. Can do the same thing, do a similar thing for f plus g. In other words, that we can write f plus g as the tangent line plus some error that goes to 0 in a strong way. Okay, so can we do it? Well, we've got f and we've got g. We just add them together, right? So we'll say, well, by the above, right? F plus g at x is just going to be the sum here, right? F of x naught plus g of x naught, oops, g of x naught plus f plus g plus f prime x naught plus g prime x naught times x plus x minus x naught plus u of x plus v of x minus x naught. Okay. What have we done? We've expressed our function, right? So we've expressed our function as a line, right? This guy is a line, right? We've expressed it as a line plus a term that even when divided by x minus x naught vanishes as x approaches x naught, right? Right. We've expressed it as a linear term plus some sort of error, some sort of thing where this guy goes to 0 as x approaches x naught, to say it more properly. Okay, so here's the English version, and here's the notation version. Okay, and so, right. Even when we divide by x minus x naught, as x goes to 0, this thing goes to 0, right? Because each of these terms goes to 0. We have limits and everything. Right? This guy here is a linear term, and notice that the derivative is the slope of the line, right? So that's this shows us that the derivative is that, right? In other words, that the derivative is that. Right, so here we show differentiability, and along the way we notice that the derivative is the slope of the tangent, the slope of that line, which is this thing here. So yeah, this is sort of like there's two things going on here. We're saying that not only is the sum differentiable, but its derivative is this. Not only is the product differentiable, but its derivative is this. Okay. Okay. How are people doing? Everybody okay? Do you want me to do it in the other way? I can do it in the other way as well, like the non-linear, non-line-like way, right? So if we wanted to do it in the non-line-like way, this sort of like more algebraic trickery sort of way. Right? You would say, well, f plus g prime x naught is defined as the limit of f plus g x naught plus h minus f plus g x naught over h as h approaches 0. Okay, and then you would say, well, look, that's the same thing as f of x naught plus h minus f of x naught plus g of x naught plus h minus g of x naught. Everything over h, right, as h approaches 0. Or if you don't mind, I can just split this up like now as this over h plus that over h. Right? And then you would say, well, each of these limits exists independently, and so I can play the, switch the order game. So I know that this thing is equal to the sum of the limits. Right, and I know that each of those guys exists because we said that each of them is differentiable at x naught, and then that's it. So yeah, so it's okay. If you whichever way you like, but yeah, whichever way you like. Either way is a reasonable perspective. Okay. Okay, let me do the second one, the product rule. Yeah. Let me do the second one. So, right, and let's do this one the sort of the left side of the board way. Right. Let's take the limit. And so the derivative at x naught is the limit of f times g at x naught plus h minus f times g at x naught over h as h approaches 0. Right? Which, if I write it out, is f of x naught g x naught plus h minus f of x naught g of x naught everything over h as h approaches 0. Okay, so right, I want to work in, as usual, I want to work in something that looks like f of x naught plus h. Right, I want to work in terms that look like this. Right, so what am I going to do? I'm going to subtract off f of x naught times g of x naught plus h. Do you guys see why I did that? Right? Because then I've got this thing, I can factor out, I can distribute out this thing, and then I'm going to have the term that I like. Okay. And as usual, I cannot just subtract something for the heck of it. I have to add it back in. So this is my cleverly chosen 0. Okay, so this is like the general strategy, right? Like work in what you have control over, right? Okay, so then we're going to look at, we've got this g x naught plus h, f of x naught plus h minus f of x naught over h. We also have something similar here. We've got f of x naught. We have g of x naught plus h minus g of x naught over h. Right? And as long as we can show that both of these limits exist independently, then it's okay, then this move is legitimate. Okay. We do have to, right, so we kind of have to sort of stop it here and say, let's consider these things independently, right? So now, the limit of this guy on the left, what happens, what is this thing? We kind of have to do the same thing again. We have to look at these things, these guys independently. So this is sort of like scratch work here. Okay, so let's look at this guy first. What is this? This limit we know exists. Let me stop. I'm writing too fast. I've achieved my goal of being able to write as fast as I talk. Harrison, do you have a question? Or you have an answer?
I have an answer.
Okay, hold on. Okay, what's this?
Fmx.
Of course. Okay, what's this? This is this of course, we know that this is true because we know that f is differentiable at x naught. What about this guy? As h approaches 0, well, is it?
G of x naught.
G of x naught, why? Why is that true? As h approaches 0, right, the term here goes to x naught. Is the limit as this term goes to x naught the value of the term there? In other words, yes?
Because differentiable implies continuity.
Very good. We have continuity, right? Differentiability implies continuity, so this is good. Okay. So each of those things, each of these limits exists, and so the limit of this, the limit of this thing, sorry, the limit of this product equals the product of the limits, right? So this thing equals g of x naught, f prime x naught. Okay. That's what we've just shown. Okay. This is the conclusion of the scratch work. That this thing, this limit does exist. Okay. And then we do something similar over here. It's easier over here because this term doesn't change at all, right? As h goes to 0, this term just sits there. Okay. So this is a constant, and this term, of course, is g prime x naught. Right. And so we end up over here. This thing goes to f of x naught g prime x naught. Okay. So both of those limits exist. And so it was okay for us to separate this thing into two limits, right? Into limit limit 1 plus limit 2, right? This guy was limit 1, and this guy is limit 2, right? And so we end up with g of x naught, f prime x naught, f prime x naught, plus f of x naught, g prime x naught. Okay. Okay. Okay, I'm not going to show the other way, I think, because time-wise, I think it doesn't make sense to. But if you want, you can run through it and see that it shows that differentiability holds, and the slope of the line that you get is going to be this. Okay. Okay. Okay, let's go on now to the chain rule. Okay. So you have a function f that's continuous, and you have a function g such that the image of f is contained in the domain of g. Okay, so f goes into R, right? You know, I, there's some domain of G here, right? And G goes from I to R, and the image of F lies inside the domain of G. So we can compose them. Okay, so we can look at the composition G composed with F, going from A, B to R. Yes?
Is G also continuous here?
No, but it will be in a second.
Professor?
Yes.
Sorry. Is I in R?
Yes.
Okay.
I is just some subset of R.
Okay.
If you want, just think of it as the domain of G. The image of F lies in the domain of G. Okay. So G, you know, F goes from R to R, G goes from R to R, but it's a different R, right? You know, the image, like that. Okay. If F is differentiable at some point x in AB, and G is differentiable at f of x, then the composition is differentiable at that point x, and as you know, the derivative of the composition is the product of the derivatives. Okay, so this this you've seen before. I almost certainly have not seen the proof of it before. So the proof, we want to show that that the limit. We want to show that the limit of g of f of t minus g of f of x over t minus x equals g prime f of x, f prime x. Okay, right, That's just the definition of differentiability. Okay. And as you might guess, the way we're going to do it is by using the linearity. Okay, we've only got. Okay, so G is line length at f of x. So what does that tell you? That tells you that G of f of t minus G of f of x can be written as f of t minus f of x times G prime at f of x plus some error term, what did I call it? V, sorry, V at f of t. Right? Is that okay? We're basically just using the line likeness of G, right? Remember that G at some point, right? So G differentiable at f of x meant that G, this was going to be G of f of x plus plus G prime f of x times this thing minus f of x plus the error guy at f of x times zeta minus f of x. Right, and I'm just plugging in the f of t for zeta. Okay. 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 And similarly, right, f is line-like. F is line-like at x, right, which tells us that f of t minus f of x is, right, f of t minus f of x is going to be f prime at x times t minus x plus the error at t times t minus x. Okay. Okay. So now let's put this all together, right? So the limit of, as t approaches x, of g of f of t minus g of f of x over t minus x, well, that's this thing. The numerator is this thing, right? The numerator is this thing. I'm going to substitute in this guy here for that. Okay, so I'm going to substitute this thing here. Right, this thing here, I'm going to put in for this guy here. Okay, so what do we get? We get the limit as t goes to x of f prime x t minus x plus u of t minus x times g prime f of x plus v f of t. Everything divided by t minus x. Okay, so what happens, right? These guys, of course, cancel out, right? You get the limit as t goes to x of f prime plus u of t times g prime f of x plus v f of t, right? But as t goes to x, what happens to u of t? Vanishes, right? As t goes to x, f of t by continuity, and here's why we had to assume f was continuous. Okay. F of t goes to f of x, and so this thing goes to f of x, right? But v, as that thing goes to f of x, v goes to 0, right? So this guy goes to 0 also, right? And so you're left with f prime at x times g prime at f of x, which is what you get. Yeah, please.
I guess this is kind of a similar question before, but do we need f to be continuous everywhere?
No, it just needs to be put continuous nearby.
Okay, cool, yeah, that's what I thought. And so then our u and our v terms, functions only have to be defined in some like neighborhood of our
That's
plane
true.
or something,
Yes,
right?
that's true.
Great.
Yeah. Easy.
Do we actually need to specify f is continuous? Because if we're assuming that it's differentiable, does that mean it's automatically going to be continuous?
Well,
It needs to be continuous at more than just x.
Oh, all over versus just at that point. Got it.
yeah,
just a
that's
little
there's
more
a
than just.
trouble. Right, so like,
Gotcha. If you said f was continuous on AB, well, yeah, that's what that means.
well, I mean, you are continuous. You might be right, Izzy. You might be right. Like,
Okay.
you've got continuity at that point,
Yeah.
right? So as x approaches t, f of x goes, I'm sorry, as t approaches x, f of t goes to f of x.
Yeah.
And that's kind of all you need.
Okay.
So, you know, there might be something tricky that I'm missing, but it may, you're like 90% correct.
Cool.
Yeah.
That's good enough for me.
Okay. Okay. So, you know, what's going on here? The way you want to think of this is just that, you know, if you have two lines and you compose them, then what happens to the slopes? The slopes get multiplied, right? That's, you got, f of x equals mx, you got g of x equals nx. Well, the product is going to have the product. The composition is the slope of the composition is going to be the product of the slopes, right? And that's what this is saying is basically that happens also, right? That your functions are line-like, right? Your functions are line-like, and so once all the errors get thrown out of the way, what you end up with is just the product of the slopes. Okay. So it's intuitively clear. Like you have this intuition that that's going to happen, and then the interpretation of it makes it clear, makes it logically clear. Okay. 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 So okay. Let me see if I can get one more thing in. Let me see, maybe I'm not going to get the whole thing in, but let's at least get the idea here. So recall that f differentiable at x meant that f equaled the tangent line plus the error. And this error vanished in this fast way. Okay. I hope you agree that the limit if u goes to 0, that's the same thing as saying the absolute value of u goes to 0. Okay, exercise. If it's not, if you haven't seen it or you want some extra exercise, then do that. Okay, so let's think. So the limit of absolute value is 0. In other words, let me call, as before, let me call this thing L of x, L of t, excuse me. F of t minus L of t equals absolute value u of t, t minus x. So notice, this is true, right? I move the L to the other side and I take absolute values of both sides. Okay. And the limit of u of t goes to 0. What does that tell us? So, what does that tell us? Right? It means that if we take any epsilon bigger than 0, there's a neighborhood in which u of t is smaller than epsilon, right? A neighborhood around x. Neighborhood around x in which u of t is smaller than epsilon. So, in other words, in that neighborhood, f of t minus L of t, which equals u of t, t minus x, is smaller than epsilon times t minus x. Okay. Graphically, what does that mean? What does that mean? That means that here's my function. Here's my function. Here's x. There's this neighborhood that I was just talking about, right? The neighborhood around, let me call it that. And in that neighborhood, the difference from the tangent line, is controlled by this slope times this linear term. Okay. What's the slope times the linear term look like? Well, if this is t and this is x, it looks like this, where the epsilon is the slope of this line. Okay. Okay. So what does that say? That says that, graphically speaking, it says that if you take this line and then you add on a slope of plus epsilon and a slope of minus epsilon. Oops. Okay. It says that the function lives inside lives inside that cone around the line. Okay. Right? That epsilon, I'm going to call this thing the epsilon cone. Okay. So, right, what did differentiability mean? It meant that if you take any epsilon cone, no matter how tight, there's going to be a neighborhood in which your function lives inside that epsilon cone around the line. Okay. Right? So like, here's my function, here's my line. It says no matter what epsilon cone I take, maybe first I take a cone of very wide aperture. there's a neighborhood of x. There's a neighborhood of x where my function stays in the cone. Okay. Or you can think of it like this is some sort of like bow tie. Okay. And your function does not leave the bow tie. There's a neighborhood in which the function does not leave the bow tie. Okay. Right. And if I choose a tighter bow tie, if I choose a tighter epsilon cone, right, like this, there I'm guaranteed a neighborhood in which the function still doesn't leave the bow tie. Okay. So this is, that's really what's going on with this thing going to 0, right? This thing going to 0, I mean this thing going to 0 is basically this cone bow tie condition. Okay, let me say it again, right? For this thing to go to 0 means that I can make it smaller than whatever epsilon I feel like. Okay. If I consider this condition here, this means that the function lives on the epsilon bow tie of the line. Okay? So for this thing to go to 0 means that no matter what epsilon bow tie I've taken, there is a neighborhood on which the function doesn't leave that that bow tie around the line. Okay, that's it for today. Next time we'll do the critical point theorem, and we'll prove like all the results in differential calculus in one fell swoop.